So, for those of you who don't know me, which probably a lot of people don't, but I've been in the industry a very long time. My name is Nathan Holmes. I am the Senior Manager of Training at the Access Networks division of Snap One. For those of you who don't know, Snap bought us this year. And to answer the questions, yes, everything seems to be still business as normal, and it should be a good thing for everybody. I have been in the industry since the mid-90s. I'm a big believer in education, both when I owned companies and worked throughout the industry. I've done a lot of different training roles. I continually improve or get new, letters behind my name. The last two would be the CWNA and the CWAP, which are wireless certifications. I believe very heavily in our clients look at us as experts, so let's try to be as close to that as we can be and stay on top of things and get the knowledge of the new things that are out. Obviously, that's why you're here today. As we all hear Wi-Fi 6 throughout the news, it started becoming, everybody are putting these APs out, and we've got all these new devices, although I'll tell you why in a little bit. Apple has 0 Wi-Fi 6 devices. How's that for a little hook to bring you in? What is Wi-Fi 6? Why does it matter? And what is this new thing called 6E? Is this something different? Is it something I need to be concerned about? That's what we're going to talk about today. So, to do that, we're going to understand this new concept called generational Wi-Fi. Why did we need new names? Why couldn't we just keep calling it 802.11ac, AX, G, N? Why do we need this? And then, what are we getting with Wi-Fi 6? Are we getting something that's worth all this talk about? Is there a reason for clients to get, upgrade their systems? Yes, and we'll talk about what those are. Then we'll also talk about this new concept called 6E. Are we going to have it today, tomorrow? When's it coming? Why do we need to, can we just change through firmware? What is it going to take for us to embrace 6E when it's here, and why does it matter? So we'll go through all that, and at the end, I want to finish up with not only does it make sense to use it now, or should I wait, along with some real basics on how to adjust your designs to ensure that they support Wi-Fi 6, because it is slightly different than Wi-Fi 5, so you need to do a little different design characteristic. Generational Wi-Fi is a new naming convention created by the Wi-Fi Alliance. Now, the Wi-Fi Alliance is who coined the term Wi-Fi years ago, and we use that in all of our daily speak, so they seem to be pretty good at understanding how to make something easy to understand. And that was the goal, because, how do we know if a phone can do 802.11ax or AC or N? How do we know what we're connected? We can tell when we're connected LTE. We can know when we're connected 5G. We got a little icon up there, right? Well, that makes it a lot easier. For customers, all they see now is, I have a little Wi-Fi symbol, so I guess I'm on Wi-Fi, but I don't know what kind of Wi-Fi. It just happens to be connected. So the Alliance said, let's come up with a new naming convention that's easy to understand. Now, it only goes back 4 generations, but the 4th generation of Wi-Fi was 802.11n, so they called it Wi-Fi 4, Wi-Fi 5, Wi-Fi 6. It's all based on the generation of Wi-Fi that's being utilized. Now, to understand, though, only companies that pay to have their devices certified by the Wi-Fi Alliance will be able to market as I'm Wi-Fi 6 certified. So that's why I said Apple has 0 Wi-Fi 6 devices. If you look at their devices, you'll have a bunch of them that are 802.11ax, but they didn't pay to get a Wi-Fi 6 denomination. Doesn't mean that they're any different. You just have to understand that, so that if a customer says, well, I need AX, a Wi-Fi 6 access point is AX. AX is Wi-Fi 6. It's just 2 different names for the same thing. One is a marketing term designed to make it easier. It is fundamentally different than all Wi-Fi before. There were a lot of problems with Wi-Fi, a lot of inefficiencies. So Wi-Fi was first created in 1997. Wi-Fi Prime, or 802.11 Prime was produced then. Since then, we fought this, fought that, so it was time to do a rewrite. One of the biggest fundamental things, and why it's called high-efficiency Wi-Fi, deals with something called OfDMA. OFDM is the modulation technique that we use on every generation before. The whole idea being, if you're doing a 20 megahertz wide, 40, 80 megahertz wide channel, whatever it is, you're using the entire channel width every time you send a transmission. Doesn't matter if it's a small packet, large packet, whatever, using the whole channel width every single time. And that whole duration of time. That's not very efficient. If you got a whole bunch of devices, they're all fighting for airtime. You know, you just want to, if I got little, let's send little. If I got a lot, let's send a lot. So that's what OfDMA does, is it breaks everything down into resource units, and then based on how much, or how many resource units you need to send a packet, that's how much spectral allocation you need. So you can do small, you could do multiple at the same time. There's lots of different ways that it can be done. This is not my clicker not clicking. I guess it's having Wi-Fi interference. But yeah, we got the clicker is not clicking. There we go. All right, let's back up a little bit. I guess it was just storing. So in Wi-Fi 6 with OfDMA, each client is only going to use as much of the spectrum as it needs for that transmission. So therefore, it's, you know, one, it can be a little high power because it's not as spread out. A lot of reasons why it's more efficient. Additionally, to make sure that they have as many reduced size needed, they broke the channel up. Originally, a 20 megahertz wide channel was only divided into 64 different subcarriers. Now it's 256 subcarriers, and they group those together in various sizes based on how much data needs to go, which means you're either using a very small portion for potentially multiple, up to 9 users on a 20 megahertz channel, or using the whole 20 megahertz channel. The idea being, why spend the whole time talking to one client if we could technically let multiple people use small chunks at the same time? It's different than multi-user MIMO, but it's still a more efficient way of transmitting. Like I said, this allows for simultaneous conversations. For anybody who doesn't know, Wi-Fi right now, up to Wi-Fi 5, one client device talks at a time, period. I don't care if there's 4,000 people connected to 4 access points, 1,000 people per access point. If they're all on the same channel, one talks, 3,099 or 999 listen. Only one device can use a frequency at a time. So if you're using that whole 20 megahertz wide channel, guess what? One device. With OfDMA though, we could break that up and each device only uses a small section of that frequency. So therefore, we can actually do multiple transmissions and multiple transmissions to an access point for multiple clients, or a transmission from an access point to multiple clients. We just have to queue them. So in high density applications, this allows you to handle multiple things all at once, which we cannot do with Wi-Fi now. Yes, we've all heard manufacturers talk about something called multi-user MIMO. I'm not going to go deep in it, but understand that multi-user MIMO doesn't work because no client devices support it. Doesn't matter if your access point does. If the client device doesn't support it, it doesn't do you any good. They don't support it because it kills battery life and doesn't provide the benefit they thought it would. Works in a lab, not in real life. So therefore, we've had no multi-user applications in Wi-Fi prior to Wi-Fi 6. This will work the same way cell phones do, so we have a use case that is proven that we can now use in Wi-Fi. That's one of the really cool things from a multiple device perspective that comes with Wi-Fi 6. All right, we'll go past all that. So, by breaking it into these small resource units and just using what you need, you can do up to 37 clients technically on an 80 megahertz wide channel. Are we going to do that in most homes? No. You're probably only going to see things like that in massive stadiums. But it does mean that the access point, this is a good thing to remember, the access point will choose how it needs to respond. If you've only got one client device there, it may just use OFDM, use the whole spectrum. Boom, send it to that device, we're done. I don't need to think about things. But as you start having more devices in that environment, it can switch to OFDMA, it can switch to smaller packet sizes, it can switch to multiple at the same time. The access point will decide how to send and receive data in that environment based on the load, based on the number of clients and the client types, things like that. So your access point has a lot more functions now than it did before than just saying you're connected. It's really doing a lot of things in the decision tree. All right, that's only one thing. What about this? Wi-Fi is contention-based, which, like we said, makes sure only one device can use a channel, right? Well, that's great. The smartphone says, hey, anybody else using this channel? No? Oh, wait, The laptop is. The laptop says I'm using the channel. So that smart device says, you know what? I'm just going to wait for a while. Once you're done transmitting, I'll send again. That's the way Wi-Fi works. Is anybody transmitting? Yep. Okay, I'll wait. Anybody transmitting? Nope. Okay, I'll transmit. Because they want to make sure that only one device uses a channel. So it's based on contention. Well, that's great. But if you've got too many access points on the same channel, whether they're in your house or in your neighbor's house, if they can all hear each other, like in this example, I got 4 houses, 3 of them on channel 1, one's on channel 6. Every single client device in those 3 houses in channel 1 that can hear each other, they wait. Hey, can I transmit? Nope, I'm transmitting. So your neighbor's houses are preventing your devices from transmitting because you're using the same channel. They have to wait their turn. The only guy who doesn't care is the guy on channel 6. So again, this is not very efficient. So Wi-Fi 6 introduced something called SSID coloring. Now, it doesn't mean you're going to have rosy, awesome Wi-Fi permeating the environment. That'd be cool, but it's not happening. What you get is there's a little bit added to the header which identifies one of a different color. So there's 64 bits, so they're calling it color, SSID coloring. But the idea is, even though these 3 APs are all in the same channel, they all have a different color bit, so now they don't have to wait for the other device that's connected to a different AP that's using the same channel. It goes, that's a different access point. I don't care if you're using the channel. I'm going to go anyways. So while there may be a little bit of interference, it's likely too far away to cause much of a disruption, so that it allows you to transmit anyways. This is going to help significantly in MDUs and other areas where you've got a lot of houses all next to each other. They're all sharing the same channel. Right now, they have to wait, so you have a high latency. With Wi-Fi 6, you won't have to wait. Very cool. Additionally, how about battery life? Everybody struggles with the battery life on their phones. So they took something that started in 802.11ah called target wait times. It says, hey, I'm a client device that can handle target wait times. Access point says, cool, I'll add you to my schedule. Another device says, I can do that too. Tell me when I should wake up. The access point will make a list of this and then send an overall schedule out to all devices saying, device 1, this is when I want you to wake up and either transmit or receive. Device 2, this is when you should wake up and transmit or receive. That allows the client device to go to sleep and not have to continually monitor the Wi-Fi environment until it's its time to wake up. Therefore, you can get up to a 67% increase in battery life, so decrease in power consumption. Kind of cool and very relevant when you're talking devices that are just sitting in your pocket. What do they really need to transmit for most of the time? So they go to sleep and wake up when needed. Now, this is the one that everybody goes, all right, how much faster are we going to be with Wi-Fi 6? Well, when you went from G to N, you got a 10 times speed increase, right? That was awesome. When you went from N to AC, you got 10 times the speed. That was pretty awesome, too. Going from Wi-Fi 5 to Wi-Fi 6, you get a 50% increase in speed. It is a little bit, but again, Wi-Fi 6 was designed for efficiency, to remove issues more than to provide speed. But it does provide a potential increase. To get that increase, it requires the use of 1024 QAM. QAM relates to the value of how many bits of information can be sent every transmission. Well, with Wi-Fi 6, we can do up to 1024 QAM. But to do so, you have to have much higher signal to noise ratio. You have to have cleaner signal. Why? Well, let me ask you a question. If I ask you to throw a dart at a dot, and that dart is 1 foot away, that's pretty easy. You're going to probably hit that dot most of the time. Well, you might miss. No, just kidding. But what if I move that dot 20 feet away? That's going to be a lot harder to hit that with that dart. Imagine how hard it is to reference a single point in space that represents where 2 carrier waves are intersecting by a single dot when you have a 1024 QAM. You have to have clear signal compared to noise in the environment for it to be able to differentiate those dots. You need to have a minimum of 3 dB more than the highest Wi-Fi 5. So basically you need 41 dB signal to noise ratio to even begin using 1024 QAM. So it requires some different design characteristics, better signal if you get or want higher data rates. If you don't have cleaner signal, guess what? You're not going to get higher data rates. It's just the way it works. So potentially could be there, but overall your client devices will likely need to be within 22 feet of an access point to receive these highest data rates. Now, here's where we get this wonderful thing, and people have got in the news. You're seeing all these reports that Wi-Fi 6E is coming. It is changing the world. It's everything. It's amazing. We have to have it. Okay, what is it? Why do we need it? Well, when Wi-Fi first came out, we knew that the first APs, first everything was on 2.4 gig. Out of 2.4 gig, we have 3 usable non-overlapping channels on the 20 megahertz spectrum. No manufacturer that should be used will use wider than a 20 megahertz wide channel. One company in our industry does. They're wrong. Overall, you have 3 channels that should be used. They're 20 megahertz. That's great, but you don't have a lot to choose from. By the time you get to 4 APs, you're doing co-channel contention. Well, what about 5 gig? There's a lot more channels, right? Well, sure, there's 25 channels, but a lot of them are shared with weather stations, air traffic control towers, some other devices that are using them. Those are called DFS channels. So while we choose to use them because that gives us 6 80 megahertz wide channels, we have to be cautious of how we're interfering with other things. And if you're using consumer products, they're only going to give you 2. They're going to give you the low 5 gig and the high 5 gig. So you don't have a lot of channels to choose from. And even though the Wi-Fi standard says we can do 160 meg channels, you do not have any space where you can really use it because of how they work. So to combat this and get us in a space where we have more frequency to choose from, more channels that we can use, the IEEE was able to convince the FCC, and this is happening around the world, to open up the 6 gigahertz spectrum. Opening up the 6 gig spectrum will give us 59 20 megahertz wide channels. Although we probably won't use 20 meg, we'll probably use 80 meg, but that's still an additional 14 80 megahertz wide channels, which is awesome. That means if you're putting a new deployment in a house, you would have to get to 15 access points before you get to the first access point that would have to reuse a channel from another access point. That's awesome. It also means that if you have tightly packed houses, you can choose channels your neighbors aren't choosing, so you're not doing co-channel contention, any of those things. This is why they're saying it's revolutionary. What does it really mean? Is it different than Wi-Fi 6? It is Wi-Fi 6, but it's Wi-Fi 6 on the 6 gigahertz spectrum. So that's what it's going to give for us, but it also makes you understand that no, this is not firmware upgradable. You will have to change your access points to get this. Does it mean your client's going to see a performance increase? Probably not, because what's our performance based on? The performance is based on the standard. He's getting Wi-Fi 6 on 5 gig, or he's getting Wi-Fi 6 on 6 gig. The maximum speeds are the same, the maximum throughputs are the same. He just doesn't get as much latency from his customers. It's hard for people to see and experience latency in the real world. So your designs will absolutely transition over time to using access points in the 6 gig spectrum. Does it mean you're going to have to rip out Wi-Fi 6 APs? No. But it absolutely means if you've got older Wi-Fi 5 or AC access points, yes, you're going to want to transition. For now, for the next 12 to 18 months, you're absolutely going to be putting in Wi-Fi 6 based APs. Give another, it could be 2 years before we start seeing a lot of 6E, and eventually you'll start using 6E. That's just the way the industry works. You're going to get newer technology. But when a client asks you, am I going to get a performance increase? Should I wait for 6E? Absolutely not. You should be getting 6 now because your client devices use 6. So give them an access point that supports their current client devices. Come on, there we go. Still probably won't be able to use 160 megahertz wide channels. This is because you're spanning 8 20 megahertz wide channels. Any device broadcasting on any of those 20 megahertz channels will interfere with your 160. Therefore, you can't transmit. So if any device is using those, you got to wait your turn. There's still contention. You still have to wait. We may, especially in, maybe in a home that's, 20 acres, can't see his neighbors, everything like that. Sure, maybe you'll be able to use 160s. It'll be on a case-by-case basis. Currently, we're going to have to wait and see how it goes. Designs, at least for the short term, will still be based on 80 megahertz wides as the max. All right. I guess I kind of dove into this a little bit already. Should you be using it now? Yes. Wi-Fi 6 client devices are already here. Your iPhone 11s, your S20s, your Samsung devices and other Androids, you'll see the Wi-Fi symbol up at the top, and it'll show a little Wi-Fi with a 5, a Wi-Fi for a 6, or Wi-Fi 4, depending on the generation it's on. iPhones will not, like I said, they're not required to because they don't meet the Wi-Fi Alliance standard. But it is kind of cool if a client comes to you and says, why does my phone say Wi-Fi 5, or it has this Wi-Fi in a 5 at my house, but it has a Wi-Fi in a 6 over at my friend's house? Their friend has Wi-Fi 6 access points, they have Wi-Fi 5. Time to upgrade them. It is the first rewrite on how it works. So you've seen some of the things, and I could go very deep in those, but overall it's all about efficiency. What do our clients really want when we sell them all of these wonderful toys and gadgets? They want to know that every time they walk away from it, it's just going to keep working. It's going to stay online. It's going to be there when they need it. They don't have to think about it when they don't need it. That's about staying connected. It's about efficiency. It's about not interfering with other things negatively. Everything about Wi-Fi 6 was built from the ground up to be more efficient, more stable, and to encourage devices to stay connected better. So as more manufacturers embrace Wi-Fi 6 and more devices become Wi-Fi 6, these benefits will become more and more apparent and better. So basically it's kind of cool. You put it in now, and the system will keep getting better over time as more and more devices become Wi-Fi 6 capable. It does provide increased data rates. You are going to see a slight performance increase. Is that what it's about? No, but of course everybody's going to go, how much faster, how much faster? You're going to be a little faster. Overall, when you're talking to customers, understand your Wi-Fi should be at least 1/3 of whatever your connection rate is. So if you get a client device that's connected at 1.2 gig, he should see around 400 meg throughput. Wi-Fi is half duplex, so he spends half its time talking, half its time listening, so there's a 50% decrease. You've got overhead, you've got management frames, so overall, usually 1/3 is a really good set point to get a client expectation. If they get over that number, great. But you want to tell them, yeah, you should get at least 400 meg. If they're getting 50 or 70 meg, maybe they're supposed to, because again, that's at 5 gig. 2.4, your maximum data rates are different. You're using a 20 megahertz wide channel, a 200 meg data rate. What's 1/3 of 200 meg? Oh yeah, about 65, 70. So if they're getting 70 meg throughput and they're on 2.4, they're doing exactly what they're supposed to. They may be frustrated in not understanding why they're not getting 400, but the device is working perfectly. So again, slightly faster data rates, understand how they work. You're going to get potentially increased battery life. You're going to not have as much interference from your neighbors because you've got SSID coloring, so you can separate those things. You're going to have a third frequency to avoid interference. Our biggest thing that we fight is interference with ourselves, interfering with our neighbors. These are all things that are going to help us over time. And it just means that the more confidence people get in their Wi-Fi working great, the more they're going to want to upgrade, the more they want to use, the more they want to depend on it. Now, to make sure that it works correctly, you do have some design considerations you have to keep in mind. Designs must be based on 5 gigahertz coverage. I don't care of the fact that 2.4 goes farther. I don't care that you can do 2.4. If all you're going to do is design a network that's 2.4, or you're going to design it to kind of support 5 gig, turn 5 gig off, period. You're going to create a bad experience for your customer. Design for 5 gig, ensure you have proper overlap between 5 gig so your client device stays at 5 gig the entire time. Does that mean turn 2.4 off? No. Client devices are designed to be dual band, at least all the disposable ones I call them, like phones, iPads, things like that. They want to be able to choose between those. So part of their decision tree is having that there. As they roam to the outside skirts of everything, they want to be able to go to 2.4 when they're on the fringe, but when they're in the 5 gig area, they stay. One of the most difficult things, and it seems weird, but the decision process is more difficult to go from 5 gig to 2.4 than it is to go from 5 gig on one AP to 5 gig on another AP. It's easier for a device to roam than it is to transition bands on the same AP. So, design for 5 gig. What does that mean? Maximum 1,350 square feet per AP, designed for 1,200 square feet. This is a reality. I would love it to be 5,000 square feet and we're done, but this is what it takes if you want seamless coverage. You need a minimum of 18 dB overlap in between your APs. This means your APs should be a maximum of 35, well, maximum 40, but you typically design for 35 to 38 feet apart line of sight. This will give you appropriate overlap coverage. And this doesn't, I'm not talking about my company's products compared to that company's products compared to this. This is how Wi-Fi functions. This is RF. This is your design regardless of which manufacturer you're using. All right, so yeah, 35 to 38 feet apart line of sight, 5 gig coverage is your requirement. Minimum 20% or 18 dB overlap. Access points must be on different channels to prevent co-channel contention. And Wi-Fi is polarized. A lot of people don't realize this, but how you install your access points is critical to determining how they are going to provide RF coverage in that environment. Let me ask you a question. If you put a speaker on the floor aiming down, are you going to hear good sound? No, you're not going to hear much of anything. So if you take your access point that's supposed to be on a ceiling, domed down in the middle of a room, and you put it on a wall behind a TV, are you going to get good Wi-Fi? No, you're going to get crap Wi-Fi. It's behind a piece of equipment designed to block RF energy, and you're putting in a piece of equipment designed to produce RF energy. They don't work well together. So think about where you're installing them. Understand that RF is radiating out from it about 25 feet in either direction and about 12 feet down. You put that on a wall, you're getting a vertical donut that's going 25 feet up, but it's still only coming out about 12 to 14 feet in front of it, almost nothing behind it. If you have to do that, great, but do it with intention and understand how it changes RF coverage in that environment, and add as many APs as you need to fill in that coverage to ensure that you stay on 5 gigahertz. Overall, everybody asks me this, what do I need to put in for infrastructure? Well, APs are now capable of multi-gigabit connectivity. Well, okay, does that mean I need to run 2 CATs? Does it mean I have to run 6A? What does it mean? Well, different manufacturers support this different ways. Some of them use link aggregation groups to do 2 gig to the AP. Some of them use N-base-T ports, so you've got 2.5 gig over Cat5e or Cat6. Others require a 10 gig connection with Cat6a or under 50 meters with Cat6. Either way, you need to understand what your APs are capable of and then put in the products that can support that. The end of the day, my recommendation differs a little bit from, say, what the industry standard. The industry standard says, 578, the CompTIA 570B residential infrastructure standard calls for 2 Cat6As to every device on top of coax and fiber, and that's what they're going to recommend. That's great if you're going to do what you need to do, which says you're going to certify each one of those cables to 10 gig. You're not just going to put them in. If you put in a cable and you don't certify it, you're not doing your customer the job you were hired to do. Put it in and certify it. Make sure your guys, you also should be doing a permanent connection. You get the warranty for manufacturing cable is about a permanent connection on both ends, which means a patch panel and a wall plate. That's the way these things work. So if you're putting it in on 6A and you can do a little patch cord to the AP, great. If you're not, I do a lot of installations where I tell them put a Cat6 and a Cat6A. What have you done? The Cat6 will give you N-base-T connectivity of 1 gig, 2.5, or 5 gig. The Cat6A will ensure that you can hit 10 gig. You've now given yourself a single Cat for each of the different speeds that all the APs are capable, and ensured your customer being able to have connectivity for at least the next 10 years, which I think is important. So that's my recommendation as it sits now, is to run 2 CATs. At least one should be 6A. The other 6 is easier to terminate right now, is easier to certify, and takes less time. So your choice, but that's the minimum recommendation for me. Overall, we've had Wi-Fi 6 APs for quite a while. We've got multiple versions. Feel free to stop by and ask me about them, whatever you want. And I'm going to open it up to any questions, if anybody has any.
I don't know if I should do stand-up. Go for it. So you're saying definitely no on the firmware update path for going from 6 to 6E?
Yeah, you're going to have a different chipset that's going to go be able to produce the 5 gig, to work in the 6 gig realm. So the chipsets in the AP are relegated to 2.4 and 5 gig. So it will be a hardware change to be able to use the 6 gig frequency range.
Got it. Thank you.
You're suggesting to run 2 CATs to each WAP, but they're not both going to be used. One is like a spare for future use?
That depends on which product you're using and what the project needs. Meaning, Some access points can do what's called a link aggregation group, where you take 2 cats connected to a switch that can also do link aggregation, and now you can get a 2 gig connection between that AP and the switch. And it's also, they work in redundancy. So if one of them gets damaged, it would still stay up and still have a single gig connectivity. If you're designing a system now that doesn't need more than 1 gig connectivity, but you've got a customer that's adamant on having resiliency throughout the network, failover firewalls, failover core switch, redundancy to every single device, yes, there is a time now where you could use dual cats to that AP to provide that solution. You're not talking about higher throughput, you're talking about redundancy to make sure there's no issue. Over time, I think it's our responsibility to put infrastructure products in that support the homeowner not only today but down the road. When they buy a house, the roof is good for 30 years. The plumbing is good for a number, 20, 30 years. The electrical is good for so many years. How long should the infrastructure we provide them be able to sustain new products? Right now, we've got APs that can use 10 gig connectivity. Therefore, putting a 6A guarantees you 100 meter on 10 gig. Putting 6 guarantees you 50 meter. What happens in, let's just say, 7 or 8 years from now, we've got things that are doing higher than 10 gig connectivity. Well, if we've got 2 cats of some kind there, we might be able to get up to 20 gig connectivity if we're under 50 meters, and we're doing a link aggregation. So my goal is to make sure that we understand you're not limited to just 6 or 6A, and think about what you're putting in, because sometimes it's not just about the AP. What about tomorrow we come out and there's a newer technology that allows you to monitor everything going on in the deployment, and it takes a different AP put in that environment to monitor. If you've already wired the house, you have no additional cat to use. If you've got a couple cats to every access point location, now you have wiring that can be used for additional functionality. But being able to explain it to a customer now, you're ensuring they have connectivity today at a lower cost of 6, or you can put 2 6As, I don't care, and ensuring they can support future technologies. So that's my recommendation. Do you have to do it? Absolutely not. You need a minimum of 1. But I recommend being able to, it's a very low cost to put a second cat in. And even if you don't terminate it, if you just put it in, don't care. It's there if you need it.
What do you think of Cat 7 or 8?
So far, I haven't faced any situation that creates a relevancy to needing something greater than 10 gig connectivity. All of the maximum, realistically right now on your access point, you are not going to exceed 1 gig. Can we within a couple years? Sure. Within the next 10, do I see us exceeding 10 gig? No. And even if we do, the 2-cat solution is there. But when it comes to putting in something like 7, how are you going to terminate it? How are you going to certify it? How are you going to support it? And does it give your client a benefit? If you're doing that, why don't you just put fiber? I can give you an access point today that uses fiber. Okay, I would be much more inclined to have you put fiber in than putting Cat 7, just because it has a relevancy in the near future. Cat 7 seems to be great when you're doing, 40 gig, 25, 40, or 100 gig infrastructure when you're talking about the connectivity between switches. But when we're talking Wi-Fi, I haven't seen it really make sense yet. It doesn't mean it won't at some point, but for right now, I haven't felt the need to go above this. Good question.
What are your recommendations for improving automatic switching between access points from a single device?
So you're talking about how do I improve client roaming?
Yes.
Design your network for 5 gig correctly. Honestly. So the client device itself is the only thing that can seamlessly choose to leave one access point and authenticate to another. Every manufacturer uses different threshold settings as to when it should do that. But again, one of the reasons I brought this up is for a client device, when it's connected to an access point, it also records the values of the nearby APs primarily on the same frequency band. So therefore, when the client device roams, it is likely going to roam to another AP on the same frequency band better than changing frequencies on the same AP. Because if it's changing on the same AP and it reaches a low threshold, and there is not another AP on the same frequency band. So if you're on 5 gig and you reach a threshold, the signal is now too low, and it needs to either roam to a new AP or change to 2.4. If it hasn't already recorded another AP long enough that it has it in its decision list, now it's going to go, oh crap, there is no other 5 gig, let me go to 2.4. That decision takes longer and will provide a less seamless roaming situation than having proper overlap. So the key is not just the AP that you're connected to, but ensuring that while you're connected to an AP along a walk path, you can always see a minimum of 1, if not 2 more access points on the same frequency band at sufficient enough signal that it can roam seamlessly. Hence, that making sure you have 18 dB of overlap, making sure that you're within certain distance before you get to another AP, and then looking at the project. If I got 2 APs that are 35 feet apart, but I've got a 14-inch concrete wall between them, I'm probably not going to roam seamlessly. But that's your starting point, and then you look close. But it is 100% about ensuring that the coverage is seamless, so when the device makes its decision, you're keeping it making fewer decisions. So if I'm on the same frequency band, but just a different channel, but I'm still in 5 gig, same authentication, you're going to have a better experience than dropping to 2.4. Great question.
How about the naming, the 2.4 gig and 5? Give it the same name or 2 separate?
Good question. So do we name both? Do we do a 2.4 SSID and a separate 5 gig SSID? My recommendation for most devices is the manufacturers have designed their decision-making trees based on dual band. So your primary SSIDs for compatibility and best performance, I recommend being dual band. But understand you've got to then look at what devices are supporting it. We have certain devices in the industry, some IoT devices, some other stuff, some remotes, that just work better when they're only on a dedicated 2.4 gig. So my preference would be to use APs that can do both single band and dual band SSIDs. Give your homeowner the ability and guest networks the ability to be dual band. And then if you need to have a specific 2.4 gig SSID, do it. If you have a homeowner that is just adamant, they don't want to listen to reality, they just want, I need to have a high speed test at any point in time. Okay, guess what? Their device could be working perfect at a 60 or 70 meg throughput speed test when they're on 2.4. They don't want to hear it. That homeowner, maybe you do need to go to a 5 gig only SSID. Is it best practice? No. But is it what you need to do to satisfy that homeowner? Sure. So that's, understand everything that I talk about ever in regards to best practice is best practice. You then have to understand enough about the technology to tailor it as your needs change on a particular project or a particular client. Best practice is designed to give you the least number of support calls, the most compatibility, but it doesn't necessarily mean you can't do something if you need to satisfy a certain customer.
If you are range limited, do you recommend a repeater for
If I'm range limited? So you're talking about, I've got a 3,000 square foot house with a single Cat 5 in one area, so therefore I'm not going to get 5 gig coverage throughout the property? Okay. I do not recommend a repeater. I recommend using mesh APs, whether or not they're a consumer mesh or an enterprise grade mesh, your call, go to that. The problem with the repeater is it increases the time for a transmission to occur because it transmits from the AP to the repeater, and then again, they're on the same channel. So the repeater, when it transmits to the client device, the AP can't be doing anything else. It has to sit there and wait. When the client device transmits to the repeater, all other devices have to be off, and when the repeater is transmitting to the AP, all other devices have to be silent. So you're increasing the amount of, decreasing the amount of time a client device can use that because you've capitalized how much of that channel is being used repeating. Mesh APs, by nature, if they're receiving a 5 gig connection, will either have a second 5 gig antenna to transmit mesh or send it out over 2.4 so that they're not utilizing the same antenna they received the transmission on. Therefore, they could receive another transmission on that same antenna while they're transmitting out, say, 2.4 or a different 5. So you decrease the latency on the environment by not using a repeater. So no, I don't ever recommend using repeaters.
Okay, following up on that. So I thought you said because Wi-Fi 6 works more similarly to cellular networks and can, I don't know, it's not multiplex, but have more transmissions happening at the same time? Was it 9 at the same time, 9 to 32 or up to 9?
Technically up to 37 on an 80 megahertz wide channel.
Okay, so would the repeater, even though it's not best practice, if it was a Wi-Fi 6 repeater, would you still have the wait and hold issue? Or could you still do, up to 36, 37, whatever you just said?
So one, no Wi-Fi 6 repeaters yet. Secondly, this is likely only going to come into play in high density environments where maybe let's say if you've got 100 clients connected to an AP, now it can make sense. Think about it this way. If I tell you transmit, wait to transmit, wait to transmit, wait to transmit, and then you go to the you go, there's a duration of time it takes for all 4 of those transmissions to occur. If, on the other hand, I say Q, 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 you can all transmit now on this frame, I'm going to listen to him at the same time, and then I'll listen to the 4 of you. Again, you had to wait to transmit to be able to be queued up at that same time, right? That functionality, the AP has to choose or not choose. Most of the time, because of how rapidly a transmission occurs, it's going to make more sense and be more efficient for the access point to do an individual at a smaller duration, shorter portion of frequency band than it is going to be to queue everybody up and wait them. When you're talking a repeater, most repeaters, at least the ones we have now, are still using the full OFDM frame. And again, if the repeater is going to get something, and let's say it's even using smaller subcarriers, it's got to queue that up and then choose to use it when the other devices are going. So it adds a whole other element of it, which is likely going to increase latency, which is the whole reason you're trying to avoid it. So 100% of the time, do not ever use repeaters that are using the same channel. Because even if we have smaller carriers, you're still talking directional traffic in one way. So if I'm sending to multiple clients, I can't receive from the repeater. If the repeater, and for instance, we could do multiple clients because they've been queued up and transmit, I can't transmit at the same time. If you're using a meshed AP on a different channel, you're not having that same combating of time because you're using different frequencies, different channels. Make sense?
Yeah, it does. The thing I was trying to figure out is if you had a Wi-Fi 6 repeater, would that be addressed partially? Not that repeaters are a good thing. That's not my intention.
I mean,
I'm just trying to figure out if when those are available,
you're going to get a bunch of marketing people that tell you it is. They're going to say, look, we can do this. It's Wi-Fi 6. Well, actually, let me take that step back. The Wi-Fi 6 solutions that I have seen from manufacturers like, cable companies, different things that are doing your all-in-one and trying to be able to extend the range in the homes, not a single one is doing repeating. They're using mesh.
Oh, okay.
One of the difficulties we had previously in Wi-Fi 5 was 5 gig only. So you were talking a different generation of Wi-Fi between 4 and 5 and between 2.4 and 5 gig. So anytime you leave 5 gig right now, you're dropping down to a different generation of Wi-Fi on 2.4. Wi-Fi 6 is both 2.4 and 5 gig. So by being able to maintain that same 1024 QAM or all the characteristics of Wi-Fi 6 allow you to change frequencies, hence a meshed Wi-Fi 6 AP that's transmitting on one frequency and sending on another would always give a better performance than a repeater, whereas repeaters are typically locked into a single frequency.
Okay, that makes sense. Thanks.
Yep.
I always hear conflicting reports on this. So, in your opinion, is there any disadvantage to using a hidden SSID?
Is there a disadvantage to using a hidden SSID? Yes. But again, do what you need to do. When you hide an SSID, all it does is prevent the access point from broadcasting the actual ASCII characters in the beacon. It's still broadcasting a beacon. Your phone just doesn't see the characters of saying it's Tom's SSID or something like that. So every SSID, the access point, every so often on each frequency sends out a beacon response for every SSID. So if you've got 10 SSIDs on 5 gig and 10 SSIDs on 2.4, every so often it goes out on 5 gig. Here's the beacon for SSID 1. Here's the beacon for SSID 2. Here's the beacon, so you have all of this overhead going out for every single SSID you created. The devices that can recognize those. They'll then try to authenticate or not, but it's designed to every so often it sends a beacon response out. So the more SSIDs you create, the more management overhead you create in the wireless environment. So is there a disadvantage to making an additional SSID that's hidden? Yes. Is there a disadvantage to hiding an SSID that's already created? In theory, no. Are there certain client devices that have probably been designed poorly that will struggle for some reason? Yeah, but that's the client device issue. Just taking an SSID and hiding it, there's no difference in how it performs. It just doesn't show up on a client's phone. Make sense? Thank you.
Would you be able to, if you can't, I understand, but make a recommendation on RF spectrum analyzer or app for use during deployment?
Sure. It all depends on your budget. And I don't mean that to be tongue-in-cheek, but if you're looking to spend, around $1,000, Wi-Spy and Wi-Fi Analyzer from MetaGeek is a great tool. If you're looking to get into more full site surveys and heat maps, there's a reason we started carrying all the NetAlly product and Air Magnet and all those kind of things. NetAlly makes a really good handheld Wi-Fi scanning tool. They even have an iPerf attachment, different things like that. That's more for validation. If you're looking for pre-project planning with full site surveys, whether it's Air Magnet, whether it's Ekahau, those are probably, in my opinion, the two best in the industry. Tamasoft makes some good things too. But I mean, I've used both Air Magnet and Ekahau. I've used them both extensively. The reason I moved away from Ekahau is their support became very, very lacking. But it doesn't mean that the product didn't perform, just their support wasn't. Air Magnet has been a great partner, and they've got a lot of different solutions. So, but again, you're talking, you could easily be in the $10,000 range to be getting a full site survey kit set up between software licensing, training, different things like that. Whereas you could get into MetaGeek and do some basic RF analysis for around $1,000. So a lot of it's how much time do you want to invest in the product, and the other thing is invest in training. When I went and got my CWNA from the Certified Wireless Networking Professionals, I learned more about Wi-Fi than I ever knew before, and learned there's so much happening with it that it finally made a lot of the site survey stuff make sense. A lot of the companies now are requiring a CWNA to even go into your site survey hardware, because you have to understand what's happening from an RF perspective to really understand what the readings are showing you. And it's easy to look at primary coverage, but looking at secondary coverage and tertiary coverage and why you would have these data rates and throughputs, that's what the full-blown site survey software will give you, that, and then the training will help you understand it.